Welcome back to Advent of Code. We're on day 15, more than halfway through. So last time we had this business with the not hash algorithm. I hope we don't have to touch that anymore because that was pretty just required a lot of reading, a lot of understanding. 15. Start music. Start the coffee. Okay, here you encounter a pair of dueling generators. The generators, called generator A and generator B, are trying to agree on a sequence of numbers. However, one of them is malfunctioning, so the sequences don't always match. As they do this, a judge waits for each of them to generate its next value, compares the lowest 16 bits of both values, and keeps track of the number of times those parts of the values match. The generators both work on the same principle. To create its next value, a generator will take the previous value it produced, multiply it by a factor. Okay, fine. And then keep the remainder dividing that. Alright, this is just a very basic linear generator, isn't it? To get a significant sample, the judge would like to consider 40 million pairs. 40 million? That's fine. I can generate 40 million. It's quite a lot, but it's fine. Okay, this is a weird way to present the input. 873583. Oh no, it says in the... Oh no, it doesn't. Okay. Okay then. So... easy enough. We just say start A equals, what was it? 873. Start B 583. Okay. And we need factor. Okay. And then we need what? The divisor, which is the same for both. Okay, those are the... Okay. So A, B equals start A, start B. So we start there. We don't investigate those values. We go to the next values. So we say for in range 40, 1, 2, 3, 1, 2, 3, 40 million. We say we generate the new value. So A equals A times factor A, and then we divide. We do modulo divisor. B equals B times factor B modulo divisor. So that's gets the new values, A, B. Now we want to compare the two strings. So bin A will be binary of A, but we ignore the first two characters and we go to 18. So that will be the first 16 digits. By first 16 digits, they mean lowest. They mean lowest 16 bits. So hang on, let me have a look at this. Lowest, so they mean the right hand. Lowest, what does lowest mean? Lowest isn't even well defined. Yeah, they mean the right hand. Okay. So would it be like this onwards? Doesn't matter if we include the bit at the start, that's fine. And if they're equal, we add 1. Is that it? Okay, it'll take a while. Rightmost, it says, for lowest. Yeah, okay, that makes sense. So it's going through 40 million of them. I mean, should be okay. The divisor is in the billions, so we're not going to find a cycle that could be used. $631. Correct. Part 2. In the interest of trying to align a little better, the generators get more picky about the numbers they actually give to the judge. They still generate values in the same way, but now they only hand a value to the judge when it meets their criteria. Generator A looks for values that are multiples of 8. Generator B looks for values of multiples of... Sorry. A looks for multiples of 4. B looks for multiples of 8. So we can use a lazy generation here. We can say we drop to 5 million this time. Okay. Okay. Fine. It doesn't look hard, although it might take a while. So that's part 1. So here we do while true, A equals that. Now, if a percent for is 0, we do we return that. So it'll just keep going into the, oh no, not return, yield. For this one is 8. So now we do a similar process to before. We don't need that. So it's 5, 1, 2, 3, 1, 2, 3 million, 5 million. Don't need that. We don't need any of this. We say matches plus equal. And it's simply that. And this will just allow it to wait until it gets a value. So it'll keep running this loop until it gets a value. Then it will halt and remember its progress. That's one of the beautiful things about generators, which is something I've not used until recent years. I never realized its power, but it is very useful. You can do all sorts of things like permutate. It's great for permutations. So you don't have to write iterative code for permutations. You can write generator code based on the last permutation. Okay, we'll just comment that one out. So run this 0. Oh yeah, that's the old matches. What? Shouldn't be 0. Whoops, don't debug. Zero. So A starts at start A. So if we make them both 4 here, then we should basically get a quarter of what we had before, right? Because we'll still get matches, it'll just happen to... Okay, if I just do this, we say if true, then it should be just the previous... what happened previously. So we should get the same numbers before. Huh? How is it different to what I've had before? While true, A equals A times factor A percent divisor. Oh no, it would be the same as before if I use the same number. Alright, try that. We should get the same numbers before. It's the same, should be the same. We should get 61. 0! That's different here. Alright, we're gonna have to start looking at these. If true, yield bin B minus 16 onwards. Okay, let's just have a look at these values. Oh! Oh, I'm not using the generator correctly. How do I do it? Is it dot generate? Ah! I get it. Gen A gen b equals, you can't do it like what I did. The generator object is it's iterable. So dot it's just next, right? Is that correct? Okay. Now, and they're not repeating, are they? Not really. Okay. Okay, so now if we change that to 540, 1, 2, 3, 1, 2, 3, we should get the same answer as before. If that works, then we can now modify it to the new problem. So we should get 631. It wants me to leave 2 spaces between these, and I don't like doing that. Yep, 631. Okay, good. Now change that to 5 million. Get rid of that. Get rid of that. Now it's part 2. So I don't know if it'll take longer or shorter. It really depends on how often they need to re-roll, but it's probably longer because, you know, you don't actually get many. Well, no, it's gonna be by a factor of 4 to 8, isn't it? Factor of 8 overall. Because we have to wait for. Well, that didn't take too long. 279. Correct. Fine. Let's put ChatGPT on the case. Paste the input there, so you don't need to use any input file. Yeah, I mean, that's a clean way of doing it. That is smart. I mean, that's how you should do it, not do what I do with the binary strings. I don't do much stuff with bit masking, so... But that makes sense. All right. So this should work. GPT. It should take the same length of time as well. I'm interested to see how ChatGPT will approach part 2. Will it use generators or will it use just ugly while loops? Yep. Okay. Generator. Generate. Okay, it's similar. It's. I mean, I guess that's an acceptable way of doing it as well. I mean, that's a more industry-friendly way. Generators might be a bit dodgy to use because they're in an indeterminate state. It's well, I don't know. All right. Anyway, I don't know how the memory usage compares. Okay, so they should be doing 5 million now. It looks correct. Yep, that's fine. 8, 4. $279. Yep. Okay. Next problem. Permutation promenade. I was just talking about permutations. You come upon a very unusual sight. A group of programs here appear to be dancing. What is this? YouTube video of... Oh, part of me knew it might be this. Yeah, this is great. This is fantastic. This is basically bubble sort in action. This is fantastic. I think they have one of these videos for every, well, for all the major sorts. At least the comparative sorts. I don't think it will work well for the integer sorting. Great. All right. There are 16 programs in total, named A through P. They start by standing in a line. A stands in 0, so on. The program's dance consists of a sequence of dance moves. Spin, written SX, makes X programs move from the end to the front, but maintain their order otherwise. Okay, the last X programs are concatenated to the front. Fine. Exchange. Programs at positions A and B swap places. Okay, I think this can all be done easily with a list. Except it would be inefficient if there's lots of dance moves, but I don't. I think that's fine. God, I don't like all those forward slashes. It should be parsable, just separate by commas, it should be fine. They're forward slashes, not backslashes. All right. Partner, written P, AB makes the programs named A and B swap places. Fine. For example, with only 5 programs standing in a line, they could do the following dance. Easy enough. And the input's not too big, so we can just do it the inefficient way. I mean, there's no... How would you do it efficiently? You'd need access to both locations, and you'd need to know... You need a hash map to tell you that if you were using a linked list... I'm not sure of an easy way of doing that efficiently. Yeah, it might actually need quadratic time. It's fine. Okay, so we've got array equals, so we want A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, and P. Okay. Okay, with open, and damn it. Split by commas. So if move dot starts with, so the easy one is, well, there's no easy one here. Okay, we just deal with each of them. So S, so we take the X programs, move from the end to the front. Okay, so array equals, so okay, split point equals int of move 1 onwards, so that'll give us the integer. Would it be? Yeah, it could be more than 10. All right, and then we just rearrange the array in linear time. Okay, fine. Elif move dot starts with so the other one is exchange X. Okay, X What do we do? Positions A and B swap places. Pos1, pos2 equals move from one character onwards dot split on the forward slash. And then we just do int x for x in. That will give us the two positions. Array was 1, array was 2 equals array was 2, array was 1. And then finally, partner, A and B swap places. Okay, partner, it's lowercase. Okay. Car1, car2 equals move. It's gonna be 0, 1. Because it's a single character. So we do this basically. But pos1 and pos2 are gonna be array.index car1. And then swap those two positions. Okay. Then what? Just print the final order. Seems fine. Not correct. Okay. Right, let's make sure I did the three things correct. S makes X programs move from the end to the front, maintain their order. So that looks okay. All right, X positions A and B swap places. Okay, and P 1, 0, 1, 2, 3. Index, and then swap those two. What's wrong? What is wrong? Okay, we just have to try the example then. Okay, they don't give the example in a nice format. Okay, we have to type it in manually. Put that on the next line. So this one they've got is S1 X3 x3 4 PEB. Try that then. So then we end up with ECD. Oh. In the example, they started with A, B, C, D, E, just to make things more complicated. Okay. E, C, D, A, B. No, wrong. So what happened here? So after the after the spin, they should be in E, A, B, C, D. Not at all. So what? Spin 1. Oh! The split point is wrong. It should be... tail. Should be tail length. And here we use minus tail. And here we go up to minus tail. Does that work? BAEDC? BAEDC, correct. Okay. OCI. Correct. Now that you're starting to get a feel for the dance moves, you turn your attention to the dance as a whole. Keeping the positions they ended up in from their previous dance, the programs perform it again and again, including the first dance, a total of 1 billion times. 1 billion times. An example above, the second... Okay, I know what we're supposed to do here. We want to not do the dance a billion times. Instead, we just realize what the permutation is. And then what? So when we've done this, we'll get a mapping. We know where they started and where they end up. So we basically can create a hash map. 0 goes to so-and-so, 1 goes to so-and-so. All right. Now, oh, this is clever. Okay, so if you want to do it, find out what happens if they apply it 1 billion times. You can instead, so if you, this is recursion, if you work out what would happen if they did it 500 million times, and then just apply that twice. that'll get you what happens to a billion. So you just keep halving it. If you've got an odd number, you take off 1 and work halve it. If you've got an even number, you halve it. This is basically like modular exponentiation. That way you don't have to... Yeah, okay. It's not easy to explain in words. So, yeah, this is a nice problem. Okay, so we want to say, so we don't care about the letters. We just want to say, we want a hash map which maps, or better yet, it can just be described as a list. So permutation equals tuple. So it's going to be so it's going to be array.index start. So where did the ith character end up? All right, let's have a look at that. That is a permutation. Right? It says the first character goes to 15, and so on. Okay. So we know what the permutation for one dance is. We could work out, if we knew what the permutation for X dances is, we could work out the permutation for 2X dances is. Just apply that twice. So you could do that. Okay, now we just need to come up with a, so we say table equals, let's say a dictionary which maps 1 to so that says one dance would equal that permutation. We need to define a method which says given product of permutation 1 and permutation 2, we basically say we apply permutation 1 and then we apply permutation 2. So let's say sorry, we don't need that. We just say P1. So that is after applying permutation 1, our array ARR looks like what it would look like if it was 0, 1, 2, 3, 4, 5 up. After applying P1, it will look like 15, 7, 1, 4, whatever. Okay. And now equals okay, we fill this with nuns and we say for I in range length array so whatever was in 0 ends up in so we say P2 I is where it ends up. So we say array to that index equals whatever was in array 1 at that position. Oh, it's a bit confusing. So P2I is like these numbers here. So for example, the first one, 15. So P2I is saying the 15th position of the final array is where the 0th position of array ends up. Okay. And now return tuple array 2. So that's the product of P1 and P2. Get let's say n, right? So if n in table, return table n. Else, if n %2 is 0, so if it's an even number, P equals get 2, and then just multiply, and then just find the product. Perm equals the product of P with itself. Else, right, this doesn't need to be it would be similar, but we just say P equals get so it'll be n, just take away 1. Over 2. So perm equals prod of P with P as before. But then we have to add on that extra 1. So prod of with 1. Okay, either way, we get a permutation. Table n equals this and return per. So if that all works, doesn't matter. Okay, yeah. Table will be memorized accordingly. So it's literally just this. Print. Oh no. Okay. P equals get perm. What is it? 1 billion. Okay. So now we just take the original start and say final equals none for start. All right, and for I in range length start. We take so A. So we take the ith character and it goes to P I index, the index of final where it goes to with PI. Oh my god, this is so confusing. PI, B, P. It should be a tuple, right? Let's run this all. Oops, not to bug. PI get what am I printing here? Right, stop printing this. Perm equals, so that is 1. Okay. Damn it. Didn't change. What happened? I think my product is wrong. Product. Given P1 and P2. So we take because we take the first permutation. That. No, this isn't right. If we apply the first permutation to no, this is not how you do it. Sorry, so we've got array equals, so we've got to basically do this twice. Applied to, so start equals, let's say start P equals list range length P1. Okay. Let's stop. Okay, use ends from now on. So array is none for Yeah. Okay, apply P1. So we say this basically. Okay, and then array2 is that. Okay, that's n. That is n. And now array2 with the permutation applied is going to be array I. Let's just call it 1. All right, try that. List indices must be integers or slices, not none type. Array. Array. Oops. 1. Okay. Huh. So it's saying if you apply this 1 billion times using exponentiation to do it faster, we would get that. And then if you apply that permutation to the first one, you get that. Okay. Let's try it. Wrong. Okay, fine. I mean, we just need to make sure our product is correct. So let's check that 1 is correct. If 1 and 2 are correct, then surely all the rest will be correct because we're just kind of building up on that. So let's say 1. Wait. Get perm. Did I also make sure get perm works? So get perm. If n is in table, return table n, yeah. I mean, this looks fine. The recursive bit looks fine. Let me make sure. Okay, so get damn it. So it's saying 2 is that. So let's see. If we started with 0, 1, 2, 3 up to 15, so we apply this permutation twice, the first character would end up in position 15. And then I can't do this in my head. All right, so let's write this out fully. 0. So let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we apply the first permutation. So that's saying, what is it saying exactly? How did we define this permutation? Yeah, it's saying where will the first character end up? Yeah. So the first index is saying the first character, 0, will end up in position 15. Okay, so 0 will be here. And then 1 will end up here. 2 will end up here. 3 will end up here. 4 will end up here. 5 Sorry, I'm doing this wrong. Start again. So I did 0, 1, and 2. Okay, 3 will end up in position 4. 4 will end up in position 3. 5 will end up in position 9. 6 will end up in 14. 7 will end up in 12. 8 9 10 11 12 There's not enough space for this. 13 14 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 will end up at 0. 15 will end up at 5. So after just applying once, we'll end up with that. Let's check that we actually get that. Just don't do that yet. Fourteen, 2, 8, 4, 3, 15, 9, 1, 12, 5, 13, 10, 7, 11, 6, 0. Okay, now if we do this again, just by hand, we're saying so start with this one. The first character okay, so the first one is 14 and it will end up in position 15. This is already looking correct. So this index 1, 2, so the 2 will end up in 7. 8 will end up in 1. 4. Zero, 1, 2, 3. This is really confusing. I've lost my train of thought. So I've done the first 3. Okay, so 4. So item 3, which is 4, should end up in position 4. Item 4 which is 3, should end up in 3. Those two swap places, that makes sense. Interesting. 3 and 4 just keep swapping places, don't they? They'll never leave their spots. That's because, well, permutation is a product of cycles, that's the thing. So there's actually other ways of approaching this using group algebra. So the 9, 0, 1, 2, 3, 4, 5, which is 15, will end up in position 9. $14. No, that's wrong. I can't think. This is too confusing. Well, so this is lined up nicely. Okay, that's lined up now. All right, so where did we get to? 8, 3, 4, 2, 14. So we did 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we're on to this one here. So whatever's in 0, 1, 2, 3, 4, 5, whatever's in 5, which is 15, should end up in position 9. That's where it should go. Whatever's in 6, which is 9, should end up in 14. Zero. No. I'm lost again. 0, 1, 2, 3, 4. Okay. 5. Whatever's in 5. 15. No, we've done that one. Okay. Whatever's in 6, which is 9, should have in position 14. So 9 should go here. Okay. 7, which is 1, should end up as in position 12. 8, which is 12, we should end up in position 2. Nine, which is 12, should end up in position 6. 10, which is 13, should end up as in position 11. 11, which is 10, should end up in position 13. I mean, this is looking correct, but I just want to do it fully. 12, which is 7, should end up in position 8. $13, which is 11, should end up in position 10. $14, which is 6, should end up at the start. And then finally 5. So whatever's at the end, 0, should end up here. All right, so that's 6, 8, 12, 3, 4, 0. 6, 8, 12, 3, 4, 0. Is that right? Okay, 2, 7, 15, 11, 13, 1, 10, 9, 14. Why have I got another 12 here? So that one was this one here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So whatever's in position 9, which is 5, should end up in position 6. Okay, that should be 5. All right, so that's correct. The product is correct. I don't see anything wrong with that. So we've got 1,000, million, billion. Is that what they wanted? Billion. Have I got the final thing wrong? Now let's have a look. So that's so P is the permutation we get. Let's have a look at that. That's the permutation. 6, 7, 1, 3, so on. So it's saying whatever was at the start, which was A, should end up in position 6. 0, 1, 2, 3, 4, 5, 6, that's correct. And I mean, if that's correct, then the rest is probably correct. None from the start. They don't give any example here, so we don't have anything to test against. What are we printing here? Stop printing stuff. But I would like to see what values we're actually using here. So we're using... Yeah, we're halving it each time. That makes sense. Yeah, okay, fine. So I'm pretty happy with the product. Manually check that more than I needed to. So the only problem then could be get perm. So they're doing 1 billion dances including the first dance. Yeah, so that's fine. Let's try number 3, because that's the one that uses the odd case. Ooh, that's weird. Oh, something's wrong here. 3 is giving the same as 1. What? Get perm 3. Huh? 3 equals get perm 1. So it gets 1 and 1. That doesn't look right. Hang on, what's going on here? Why does it think 3 is the same as 1? Oh, and it... What? It can't be, because it's not a swapping. It's not purely a swapping. It's a shuffle. Okay, something's wrong here. So if it does... Okay. So P equals get perm 2 divided by 2. Okay, so this is going to be get perm 1. So we do prod of P and P, which will be get perm 2. Well, it'll be 2, the 6, 8, 12 one. And then it will be the 1 one. So we apply that, and then we apply that. Why have we reached that? That can't be right. So we've got this line here. It's saying, that can't be right. Hello, Buck Plugged. Thanks for the support. It's saying that the product of this permutation, that permutation, gives the same as the second permutation. That's very, very wrong. How could that happen? Alright, we just have to comment all this stuff out and just see what's precisely what's going on here. 3, get perm 3, okay, so... Okay, so we want... print... 1... R1... print... 2... 2... print... P1, P2. Try running that now. Alright, so we're trying to multiply these two together. Hello, Nihilus Red. So we apply... What am I coding? I'm doing Advent of Code 2017. Let me paste the link. It's a coding challenge. This one involves permutations. But you won't be able to see part 2 because that's the one I'm doing part 2, but you only unlock part 2 after you've done part 1. Basically, you have a permutation and you have to apply it 1 billion times, which you can't do because that's too many. So you have to do exponentiation, it's getting a bit complicated. I've only just recently started programming in Python. I really took an interest in Midas. What's Midas? Okay, I'll have a look at this. Monocular depth estimation. Depth, compute depth from a single image. What, like the physical depth in an image? Or does this depth mean something else? Pretty much yes. Cool. Monocular implies that from only one angle. I see, yeah. Nice. What, and your fork is doing it for a video? Okay, so I see. All right. Basically, I want to add 3D fog, volumetric fog, similar to how people do it in CSGO videos. Oh, so you take a video that's already been filmed and add fog in post-production. Oh, that's pretty cool. I think I'm gonna have to do this calculation by hand. I don't see what's going on here. So that, okay, so we're trying to multiply that permutation by that permutation. So if we apply the first permutation, do we get that? Let's test. So the 0th item which is 0, would go to position 6. 0, 1, 2, 3, 4, 5, 6. Alright, I'll try the last one. The 15th, the index 15, which is indeed the number 15, would go to position 14. Indeed it does. Okay, so I'm guessing that's correct. Now, we apply that permutation there. So we're saying the 0th item, 5, oh, I see what I've done wrong now. Array 2 is not the permutation in permutation notation. Array 2 is just where the elements will end up. So now, to get the actual permutation, we have to compare array 2 with start and see where each index has gone. And none for underscore and range n. Yeah, the reason I don't normally do none times n or something like that is because if you put objects in there, then if you change one object, it's going to change all the others. Although I realize in this case that clearly wouldn't be an issue. But I just like to get into the habit of that because it actually matters when you're doing, for example, mat equals none for I in range n, and then you want to create a two-dimensional matrix. I mean, this is how I create two-dimensional matrices. But you can't do it like I don't know, like using times by m or whatever, because then if you change an element in one of these rows, it will change the same element in all the other rows because they're all referring to the same object. So doing this ensures they're all separate objects and have their own memory locations. What's your take on something like PEP8? An acquaintance of mine said that you should only code with PEP8 in mind and nothing else. What what's the word? I forget the term for this. The style. I mean, my IDE is using pep something, I guess. I don't like how it keeps wanting me to leave extra blank lines between these functions. I think that's just wasteful. But aside from that, I don't mind most of its suggestions. Like, for example, its casing on variable names and stuff. I'm pretty happy with most PEP8 rules. I don't like all the additional spaces it's asking me to add. It seems like just a waste of space. Like, see here, it doesn't like me doing this. It wants me to have two spaces after before methods. But I just do it without question most of the time because it's a standard and nothing in it particularly bothers me. Everything in one row if I can. Yeah, I mean, sometimes I really do want to put some things in one row because I feel like they really should be in certain cases. But in most cases, I try to split things up as much as I can. All right, I think I know how to finish this. So okay, so now we need to look at the... Okay, so we need to do basically what we did. This is the line. Tuple. So we need to look in array2 dot index, and take whatever was what was in start and find where it ended up. That was my mistake, I think. Yeah. Sometimes I look at people like Nihui and I just get baffled by how human could come up with such code. I don't know. Are they a coding streamer? Okay. I mean, it doesn't look... I mean, it doesn't look particularly baffling to me. It's just, it clearly took a long time to build, step by step. So but I don't know much about what this is, about this library or anything. But the code itself doesn't look baffling to me, to be honest. It's just, I can believe if I built all that myself, then I would understand it. But it would take a long time. All right, let's try and run this now. So, okay, so now we get 9, 8, 12. Okay, that looks promising. So we're saying 5 ends up in position 6. Now, whatever's in position 6, 0, 1, 2, 3, 4, 5, 6, will end up in position 14. So 5 should end up in position 14. Indeed it does. Okay, this might be correct. This might be the correct answer, and we'll be done with this permutations nonsense. Nah, I like permutations. It's just, it's abstract algebra. It's never easy. Is this Python charm? Yeah, PyCharm, yeah. It's a decent IDE, I think. All right, F, B, C, D, E, G, A, H. Okay, that's hopefully the answer. Would you suggest it over VSC? Visual Studio Code? I mean, I use Visual Studio Code mostly for opening configuration files and just if I don't have an IDE for a certain language, but it probably, I mean, VS Code is probably just as good for Python. I don't really know. I've never tried using it for Python, so no comment on that really. I normally just use it for as a default if I don't have something for a language. Increase the FPS to 60 and double the bitrate. I mean, I do that for video games, for like shooting games and stuff, but for programming, I leave it low because I had some viewers say, like people who view on phones, for example, the Twitch app is garbage, so they can't really view 6,000 bitrate streams that easily. I mean, there's not many of them. Most people can, but I've had a couple of people who said my stream was just a black screen because they can't handle such high bit rates. If I do shooting games, I definitely do 6,000 more, sometimes 9,000 to 10,000 bitrate. But I mean, for programming, I've looked back at the video and I don't notice any difference really with a bitrate of like in the 3,000 range. So I just stick with whatever's going to make it easiest for people to view if they want to view. It also makes the file size of the video much smaller. And because nothing's moving much, I don't really see that 48 to 60 FPS making much difference. I mean, I definitely don't want to go as low as 30, but 48 upwards, I think is, it looks fine to me. I always try to put my bitrate as low as possible without sacrificing quality, just so to maximize, you know, ease of use for people. All right, let's try pasting this in. So last time I had, it seems a tad blurry. No, it shouldn't be blurry. That would be, I mean, nothing's moving, so it can't be blurry. That must be a Twitch problem. Hang on, let me bring up Twitch on my own. All right, let me finish this problem first, and then I'll have a look at my end. Damn it, it's wrong. F, B, C, D, E, G. Okay, it's still wrong. Man, I thought I had fixed that issue. Okay, so it's not... That wasn't the bug, but we fixed a bug. Okay. Regarding the stream, okay, I'm gonna have a look, just because you could be right. There could be something wrong somewhere. I'll just quickly bring it up on my browser. And you've set it to 1080p 48, have you? Yeah, it looks perfect to me. Just completely crisp. No blurriness at all. Yeah, so I don't know why it's blurry at your end. That's weird. How could it be blurry at 1080p? Like, it's blurry if you go to lower resolutions, but I don't... Because there's like literally nothing moving. Blur is normally caused by movement. That's weird then. I don't know what's causing that. Okay. Do I work on any bigger projects? Not... Like, lately, not really. I've mostly been doing this. Advent of Code, and another website I do is Coding Game, which has lots of AI... 27-inch screen maybe with 1080p content on full screen. I don't know what that would look like. Do you normally watch like 1440p or something? Yeah, it could be that it's just stretched out, but yeah, my monitor is 1080p, so I can't actually make a canvas of it any larger than that. Actually, I might be able to. I'll look into that. Like, I think it can be done even if I don't have a monitor of that size. It can just be scaled up. Because that might actually make it look nicer in the videos. Coding Game. Yeah. Coding Game is... Hang on, let me bring it up. This website here. It's called Coding Game. This is... I mean, in my opinion, this is the best AI coding... how to describe it? Competitive AI coding site, I guess, is the way I would describe it. There's lots of puzzles and competitions. You create bots that play a game, and then your bots are pitted against other people's bots. I mean, there are some websites that do this already, but they focus on one game in particular. But this, they release new ones every few months, and everyone can compete in them. As an example, the last one I did was this one, which I can't. Oh no, this one. But it doesn't show me the Oh, because it gets moved to this section here. Yeah, this is a really good interface as well. Like, it's really clean UI. It works like you can play your game. Okay, so I've got code here. This is from my when I enter the competition. So if I run it, this is the code I used in the competition. And then you can just run it live. You can pit your bot against your friends in this option down here, or against the boss. Each league has a boss. If you beat the boss, you move to the next league. Or the logging is down here. You can see what happened each turn. You can even log from your bots visually, so you can have your bots have a little thing above their head saying something of your choice, so that makes it easy to debug visually, saying I'm heading east or something. I don't know. The best performing, most efficient code wins. Yeah, you get ranked on a sort of ELO scheme, like in chess or something. So it's when you submit your code, it pits you against lots of people, and then it has some sort of momentum factor. So as it tries to find the right place for you by pitting you against each of those people, moving you up or down according to your wins and losses, and then it stabilizes you at a certain position. And if you submit a new code, it does that whole process again. So that's how it works out everyone's rank. So I'm in the Bronze League, for instance. I can see that you use classes in your code. Is it something you usually need to use? I mean, there's no requirement. Literally whatever you submit gets used. But I mean, it would be recommended, because as once you get into the higher leagues, you kind of need to separate things out a bit, and also sometimes you need to remember variables and states of the boards. So I wouldn't really want to do it without classes, but I mean, at the end of the day, you could write whatever your code you want here and submit it, and as long as it actually computes an answer, that's fine. All you need to output is the commands you give to each bot, where to move each turn. Where to move, what to do, what attacks to use, or whether to harvest resources or whatever. It depends what the game is. And this one was sort of like a RTS kind of game. Well, not a turn-based strategy game where you have to send ants to collect resources and just do it more efficiently than the enemy, but you can actually interfere with the enemy, so it's not like you're playing an independent game against the opponent. You can take resources that he might need and so on. Have you ever tried multi-threading? I've never really... No, not really. I've not tried much multi-threading. It hasn't really interested me that much, but... I mean, for these sites, it's useless. You can't really... Oh, it's not useless. I think they might allow it, but it's not... It doesn't give you much advantage, at least in these sites, but I mean, in Python, it's not easy, is it? Multi-processing is... I've never fully understood it, because they've got the global lock thing, which I've never really understood. I mean, when I was doing a PhD in bioinformatics, we had to use Python for multiprocessing. We often hit obstacles because of the way it does it, and sometimes we had to switch to like Cython or Jython just so we could get around that. Concurrent futures and threading are, from what I could tell, one and the same. I don't really know. I don't remember my older operating systems classes from back in the day. It was never my strong point. Butt plugged. This is 2017. Yeah. Okay, so we have a bug still. So we're saying that if you take this permutation, multiply it by itself, against itself, a billion times, we'll end up with that. Seems plausible to me. Seem to have skipped 2017 for some reason. Must have been the year I had a girlfriend. Oh, okay. Well, so far it's on the easy side, I think, compared to the last 2022 and 2021. Oh, no, I didn't do 2021. I did 2020 and 2022. So it seems easier than those recent ones. All right, Nihilus Red. Catch you some other time, maybe. I'll be continuing with this like every 2 days or something. I did the last couple of years, 2015 and 16. I mean, did you do those in the years they were released, or you just did them several years after? What's the task for 2017B? So the task for 2017B is you do that whole dance that they've described, but you have to do it a billion times. So you can't just simulate it a billion times, as you might expect. So I'm trying to use exponentiation to multiply this up, because if you can do a dance one time, you can do a dance 2 times by multiplying by itself. Then you can do it 4 times by multiplying by itself against itself again, then 8 times and 16 and so on. So you should be able to get to a billion without difficulty. I am hitting a problem though. Getting wrong answers, it seems. All right, I think it would be cleaner if I make a, I'm gonna do 2017 just now. Okay. 17A. All right, yeah, it's not, doesn't seem too hard. It's just applying their rules for each command. Oh, and thanks for the follow, Nihilus Red. I guess you might have left already, but thanks for the follow. Alright, so I have to debug this. Okay, so I need a method which says define apply permutation to an array. To an array. Let's call it R. Because I keep doing this on the spot and it might be wrong in 1 or 2 places. So we want to say okay, so array is just a fresh array. Then we want to say for I in range n, so the array, apply the permutation so the p-ith index of array contains the original ith item. That's how the permutation works. Okay. Return array. Alright, that's gonna be confusing. Let's call that array 1. Okay. So instead of this, we say array 1 equals apply p1 to start p. Okay, array 2 equals apply permutation 2 to the result of the previous permutation. Return that. Okay. And then down here, we want to say final equals apply p to the original array. Huh. It gives us a completely different result. Okay, let's just try it, but that just makes me less confident now. No, it's wrong. Okay, right, but at least we've... Oh god. At least we've unified this. Instead of doing it multiple times in different places. Okay, so now what? Ooh, could actually... Oh my god. No. Okay, fine. So yeah, we should stop using arrow because that changes. So let's change that to start. That was really stupid. That to start. FBCD. Okay. That's what I entered before, and it was wrong. Okay, fine. All right. Now what? All right, here's the ultimate test. We want to check that if we apply all right, so I've computed apply p. All right, here's a test. Now, if we do apply all right, down here, we want to test all this. So we want to say print apply, so we want get perm 1 to the original array, which is start A to P. We should end up with AOCIED. Oops. Hang on. OCIED PJBMFNKHLGA. Okay, so that get perm works for 1. Let's try 2 and 3. Okay, so let's think. Let's test whether 3 is actually what you would get. So print apply get put 1 start, and then apply get perm 1 to the result of that. And then, one more time, apply get point 1 to the result of that. So you're just doing it 3 times in a row. Check that these two are equal. So, and then the other test I need is just do it like this. Print, apply, get perm 3. So I'm saying if I apply three permutations to the start, that's the same as applying one permutation, one permutation, one permutation. This is testing whatever the term is. Well-definedness or something, I don't know. All right, let's check. Those two are equal. Okay, fine. So this would seem to work. It doesn't work for a billion. I'm on the wrong day. Oh. Did I say problem 17? No, oh, sorry, it's problem 16. Advent of Code 2017, day 16. Did I? I can't remember if I even probably thought of the year. Oh, okay, yeah. God. We've tested 1, we've tested 2, we've tested 3. And then everything after that is just using 1, 2, and 3, but adding them together and stuff. So how do we test it works for a billion? Is that even a billion? Let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, yeah. Okay. Let's see what numbers we're using here. So we're using a billion, 500 million, 250 million. It's just halving each time. Yeah, that's what we would expect. Until it gets down to 1. Oh dear. How do we debug this? I mean, I've made this functional, so it's a case of testing each of these three methods separately, but... Are you doing A? Don't know what you mean. Well, like part A, the first part. I've done part 1. I'm on to part 2 now. Yeah, I've done part 1. I just have to go through these methods again. Alright, so apply. So we create a fresh array. And we say array p I equals array I. Looks correct to me. And then we return that new array. Okay, I'm happy with that. We've sort of tested it too. Right, prod p1 and p2. So start p is just the integers from 0 to n minus 1. Array 1, we apply permutation 1 to the start. And then array 2, we apply permutation 2 to that result. And then we return this, which is saying the index of where the starting number is gone in the final array. That is our permutation. That looks fine, to be honest. And I've tested it for 2 and get perm 2 and 3. So then the big upper level method here is the one that puts it all together. If we want to apply permutation n times, if it's even, we split it into 2. So p will be permutation half as many times, and we simply do the product of p with p. And we get a permutation. If p is odd, we subtract 1, then halve it, and then we do prod p with p, and then we prod that with get perm 1, just 1. So it's p plus 1 should be n, give us n. I've tested that for 3. Do I need to test further? Then we return that permutation. So what is wrong? Right, I could do a test here where I actually just go back to the original part 1 code and do that over and over again and see that I get the same results as this get perm. I mean, we shouldn't need to, because now we know what... I mean, this is already confirmed by this, basically. We're applying get perm 1 to the start. And that gives us OCIEDP. That's OCIEDP. Yeah, that was the answer for part 1. So get perm is correct for 1. We're happy with that. I don't know. Let's try this then. So this is try get perm 3. Let's add one more to this list. We say apply get perm 2 with get perm 1. 2 plus 1 is 3. Let's check that. JMH, JMH, JMH. Yeah. So those 3 different ways of computing it all give the same result. So why... Do you have enough tea? Well, I've just been drinking coffee. I could make another one, but I don't have many coffee packets left. I mean, it's almost dinner time. I might have to switch to beer. I don't like finishing a stream without having finished a problem, so this might be the first time I have to do that. Can't think where to go from here then. Okay. Dinner time. You're not in the UK? No. I'm in Malaysia. I don't live in the UK. I'm just from there. But UK is a depressing place to be right now. From what I've heard from my UK buddies. You're in Holland. Nice. I think I probably applied to a job at booking.com before in Amsterdam. Seemed like a nice place to live. Didn't get the job. I would have taken it over London. I ended up getting a job in London at Amazon instead, but I honestly would have preferred booking.com, even if it was a... I mean, it's still a pretty well-renowned company, not quite as much as Amazon, but quality of living is more important than the company reputation. It's a little too busy in Amsterdam for me, but it's certainly more pleasant than London. Yeah, exactly. London, oh my god, it's just... I did London for like 3 years, and I was like, I can't take it anymore. Like, this is just not my cup of tea. I guess I'll have to manually check that this JMH thing is correct. So let's... Alright, so let's see. We want to apply this permutation 3 times. So where will A end up? So whatever's in position 0 goes to position 15. So A, after the first permutation, ends up in position 15. The end. Alright. Then, apply this whole thing again. Whatever's in position 15 goes to position 5. So A ends up in position 5. 0, 1, 2, 3, 4, 5. Here. And then finally, whatever's in position 5 ends up in position 9. 6, 7, 8, 9. So A should be in position 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's correct. And I mean, by symmetry, all the rest probably are in the correct places because it's a for loop and it's just... So what could have gone wrong? So I think that's correct for 3. So what goes wrong when I try to go higher than 3? Something's wrong with what I'm doing here. So when we do 7, we'll do 3, 3, 1. That sounds fine to me. Alright, if this permutation is correct, are we getting the right letter here? So it's saying A should go to position 6. 0, 1, 2, 3, 4, 5. So yeah, it does. You see. Let's just try and paste it into the website one more time. Like, just make absolute sure. No. The more often you get it wrong, the more nerve-wracking the pasting get for me. Wait, what do you mean by that? The checking of the answer on the website. Well, I mean, it's not like the time limit. It's not like they increase the amount of time, but each time it's usually just 5 minutes between submissions. See, they don't give any example here, so I can't even test it against their example. Alright, we've got to stop using shadow variables. Maybe something's going wrong with that. So let's say... let's call this px, just to make sure we're not reusing it somewhere. Px. Okay. P. Well, that's fine, because we're defining P here. Oh my god. Alright, I'm stumped. My code looks good, in all honesty. If there's a mistake, I feel like it must be right here somewhere, right in that section there. I don't know, let's try printing some for I in range, I don't know, 10. C, maybe something's going wrong here with some repeating, going around in a circle or something. Ooh? Maximum recursion depth exceeded. What the heck? Ah, no, we can't let I ever be 0. Oops. Yeah, I is not allowed to be 0. Okay, yeah, that's fine. Alright, stop printing these numbers. Okay, so that's... One, 2, 3, 4, 5, 6, 7. Now, there is a theorem in algebra that every permutation is a product of cycles, which is kind of obvious if you think about it. So you can see already that there's 3 and 4 are just swapping places every time. So 3, 4, 4, 3, 3, 4, 4, 3. That's correct. So we know after a billion times, we know whether it's going to be 3, 4, 4, 3. And indeed it will be 3, 4 because a billion is even. Okay, so those two numbers are correct. Absolutely correct. 3 and 4. Now the other cycle is 15, 5, 9, 6, 14, 0, 15, 5, 9. That will cycle. So actually you can apply this logic to each of the numbers. This is the smart way of doing it without having to do exponentiation. You just break a permutation down into a product of cycles, and then you would know exactly what each of the numbers is going to be by just identifying the cycles. So we could actually just by hand work out what a billion is going to be, because for some reason this exponentiation isn't working. So 15, 5, 9, 6, 14, 0. So billion. One, two, three. I'm gonna have to make sure I'm using the right number here as well. So 1,000,000,000%. What's this cycle's length? So it starts at 0. 0, 0, 15. So 0, 15, 5, 9, 6, 14. That's a cycle of 6, and then it goes back to 0. If we print a billion modulo 6, it's 4. So in the billionth, it should be 1, 2, 3, 4. It should be 6. Indeed it is. Now you could just do that for every digit and you basically worked out by hand what a billion should be. And that would be correct as long as each of these are individually correct, which we could also verify by just going back to the original input and just doing that n times. Just avoid calling our permutation method. If I do all of that, I'll be able to construct the final billionth by hand. And it may be different to what this method has given me. I can't think why it's not working. So do I want to do that now? Not really. But I think I've sort of theory crafted how I will solve this next time. But this is annoying. I don't know what went wrong with this recursive method, but so yeah, I'm quite confident 6 should be there. And if we look at the other ones, so 7, 12, 8, 2, 1, 7, 12, 8, 2. Okay, so the pattern is 7, 12, 8, 2, 1. Five. So we should end up back at 1. Indeed we do. Okay, good. And then we go 1, 7, 12, 8, 2. 1, 7, 12, 8, 2. So we should end up at 2. Indeed we do. 3, 4. So the first 5 digits are correct here. And then we've got 9, 6, 14, 0, 15, 5, 3, 5, 9, 6. Oh, this is confusing now because it's not aligned. 9, 6, 14, 0, 15, 5. I can't be bothered to do this for every digit, but I mean that process indicates that that's correct. So what's wrong here? So the only explanation is either we're not translating that into the letters correctly, which I can verify manually, or these first 10 are somehow wrong, which I can also verify manually. So that's what we do next time. I think I need to eat now. Oh, did I have the wrong window up? How long was that up there for? It should have been on this window. Okay, that would have looked weird. Alright, so it's gonna be something very basic, but I mean I scrutinized this. I feel so confident with this code now. Everything's pointing to it being correct, but the website's always correct because lots of people submit things, and if there's ever a mistake, Eric fixes it. So there's something wrong in my code, that absolutely, but I just don't know what it is. That's always the case. It's just it's normally they give an example and they say in the example you can test it on the example, but this time they didn't give an example. Really? Well, they sort of did. But their example was 2 instead of... Welcome back to Advent of Code 2017. So last time I got stuck on problem 16. And last night, about maybe 5 a.m., 6 a.m. in the night, I woke up with a jolt and realized exactly what I did wrong in this problem. And it's also quite... It is a very clever problem, now I realize. Well, it's not very clever, it's just, it's a smart problem and I overlooked something very important. So let's see if I'm right. So this is what I had last time. So we have these commands and these commands involve moving things around in the array. So what I did was I kind of enacted all the switching around, the swaps, and then I arrived at some final permutation of the original array. And so my assumption was that whole thing condenses into one permutation. So if we do this dance, this is a dance. If we do this dance a billion times, we just have to apply that one permutation a billion times. And that seemed logical. Except there's one catch. And that catch is this command here. I didn't take into account... Okay, let's go through the commands one by one. This one is taking the right-hand part of the array and sticking it at the front. So that's a positional movement. That's fine. This one is taking 2 locations and swapping them. Another positional movement. That's fine. This one is taking 2 letters and swapping them wherever they may be. That is not a positional movement. That changes each dance because let's say you're swapping A and B. In fact, let's print these. I want to see what we're getting here. So if A and B are the front, then you swap 1 and 2. You swap the first 2 positions. But the next dance, A and B may not be at the front. They may be in different positions. So that means the dances are different each time. So this one permutation we arrive at is not the unique permutation that describes every dance. Every dance is different. So that complicates things. But the other thing, which is interesting, is that these are commutative. So you could do these and these in any order. You can't do these 2 in any order. But you can do all the positional movements, and you can also do all the letter movements separately, because it doesn't matter. Wherever A and B end up, you can still swap A and B freely. And that's as if you swapped A and B to begin with, and then moved them about. These movements commute with these movements. So we can do a billion of these moves, and then separately we can do a billion of these. All right. And then those do boil down to permutations. We just have to, well, sort of. The letter swapping isn't really a physical movement permutation. It's a translation table, basically. A becomes some other letter, and so on. So we can do this. Now, before I do this, I want to see what swaps we're actually getting. Because there could be a nice simplification here. So let's say print swap car1, car2. All right, let's look at this. All right, so we've got there's quite a lot of them. HP, KF, NB, JK, OC, FL, JO. Okay. So So it ends up being a permutation of the letters. Oh dear. Okay, fine. But if we do a billion of those, we know what we'll end up with. So this... Okay, so how do we actually do all this? We need to handle all these separately, so... It's a different kind of permutation. That's what's confusing me though, so... How do we... Oh, I think ChatGPT will fail this. I hope he does, because this was quite tough. Alright, so we know what the permutation for a billion... Okay. Okay. Part 2. Start again. So we take this. Let's just take this. Part 1. Alright, so we've got a bunch of kind of like permutation methods now. Alright, just block this out. Alright, so this... to part 2. Do all this again. Just clean slate. Alright, but we take this out. So we only do the S's and the X's. We skip all the P's. So this will give us the positional movement. And then separately we can do the letter changes, alright? So we say permutation say P equals tuple okay, and then we do this. Okay. So if we want to get 1 billion, we do the, just say this, movement perm equals the 1 billionth. So this is ignoring all the letter swaps. And then just do this. Apply P to the start. Print that. All right, let's just try that. We don't need to print all those swaps. So that's what we get if we ignore all the letter swaps. Now, just do the letter swaps separately. I mean, there's probably a cleaner way of doing this, but we do this again. Or at least we do this again. Okay, array equals that. Take these ones out. So now we do the letter swaps. So we end up with a new alphabet. So A is mapped to whatever's directly below it and so on. This doesn't seem right. Hang on, let's just print out what we get. I'm interested. All right, so so ABC, so up to P gets remapped to this. So this is saying A goes to C, B goes to I, C goes to E, and so on. This is not the same as a permutation. So if we were to multiply this permutation by itself, let's call these translations instead of permutations. This is, can't think of a better way to describe it. A gets mapped to C, B gets mapped to I. Now, if we were to multiply this by itself, A would get mapped to C, and C would then get mapped to E by applying this again. Yeah, okay. Let's just say T equals T is a mapping. That's just easier to visualize. So A goes to C, B goes to I. Now apply prod. We will need a new product. So we need define prod. Let's call it prod T. T1, T2. So we've got one hash. We've got one map, we've got another map, we want to combine them. So in the first one, A gets mapped to C. But then when you take C from the T2 and see what that gets mapped to. Okay, so T3 equals that for K in T1 dot keys, T3 K equals T2 like that. That's the easier way to do than what we were doing before. Okay. Let's get rid of all this stuff. Okay. And now we can just do exponentiation. So we can say get translation using table 2. So if n is in table, return the table. It's the same thing. If n2, then t equals get tran n/2 table. So these all become get trans. The prod T is swapped in. Use T's instead of P's. Okay. So I'm going to say tran equals get tran. So we want 1 billion again. Okay, let's see what that looks like. T, cannot access local variable. T. There we go. T2, T3, whoops, that should be T1, T2. No, it should be T2 outside, T1 inside. You apply T1, then you apply T2, and you end up with T3. Oh my god, why do I keep typing 3? There we go. So we should end up with it's mapping A to A, B to B, C to C. Now that's actually possible if a billion is a multiple of every kind of cycle length. So it is actually possible. If the cycle lengths are, say, of size 2, 4, 5, anything which divides into a billion, then that's possible. But not if there are cycles of length 3 and 7. Weird. Are we sure about this? So it's saying that the letter swaps don't matter because they all cancel out. So if you were just swapping A and B, then next you would swap B and A back. So yes, after a billion times, you'd end up with A, B in the original order. That wouldn't happen if it was A, B, C being... Alright, let's pretend that's correct. In which case, the answer to the original problem would just be this, LabCon. Let's try that. I don't think it would be, though. I think they would have 3 cycles and so on. Not right. No. Okay, something's wrong with this. This shouldn't be as simple as that. It shouldn't simplify to A, B, C, D. The most important thing is prod here. Is prod correct? T3 is an empty map. So for K and T1 keys, so T1K would be the value that it gets mapped to in T1. And then that would be the key in T2. And the value it gets mapped to, we're condensing the two. So we end up with the keys from T1 and the values from T2, which looks okay. Something doesn't seem right though. Okay. For I in range 10, print get tran I don't want to include 0. One, two, three, they're all the same and it doesn't, what is going on here? If A maps to C and C maps to E, then the second one should be A mapping to E. Alright, do something simpler here. So we've got T, Now we need to test prod t. Print prod t t with itself. So we've got A maps to C, B maps to I, C maps to E. And then we end up with A maps to E, B maps to F. Is that right? So A maps to C, which maps to E. So we get A to E. B maps to I, which maps to F. So B to F. That's correct. So that should be 2. How on earth do we end up with... If n% 2 equals 0, what the heck is... Oh. What? Why that? Okay, this is wrong. Get tran. I didn't put brackets correctly here. Let's try this now. That's what the weird generator thing was doing. Right, so... A maps to E, B maps to F, C maps to N. So E maps to N, so we should end up with A maps to N for the number 3. Why do we get the first one again? Didn't I have this problem last time? What was the issue last time? Oh, no, because I'm printing other stuff. Okay, this is a mess. Just comment out all this stuff. Okay, go back. All right, so this is... Okay, 1. This is 2. This is 3. A to N. So A maps to C, C maps to E, E maps to N, so A to N. B maps to F, F maps to K, so B to K. That looks correct. Then we get A to P. So it goes A to C, A to E, A to N, N to P, A to J, B, I, F, K. Interesting. Let's increase this to 20. So we should find all the cycles now. So A is just cycling about. Okay, yeah, okay, fine. So that means after billion, how big are the cycles? We shouldn't end up with A, should we? 10. A maps to A. Okay, it does. Okay, A returns to A. B returns to B. C returns to C. So lots of the letters just actually map back to themselves in number 10. Cool. The only ones that don't are D mapping to L. So what goes on with D? D goes D, G, L, O. That's a cycle of 4, D, G, L, O. So what billion is divisible by 4? So D will return to D. Correct. Okay, so A, B, C, D, E, F. G goes G, L, O, D, G, L, O, D. That's 4. H goes to H, I goes to I, J goes to J, K goes to K, L goes to D, M, N, O, P. Okay, I think we've proved that if you do a billion of these letter swaps, you actually get back to the original alphabet, surely. So what do we end up with? So if we assume that's correct, that looks correct. I mean, I've sort of verified it by eye. Then that labcon should be the answer, shouldn't it? I mean... So how do we get labcon? We're basically ignoring the letter swaps because they cancel out. So we just take the S's and the X's. Oh! That should be perm, not P. That will give us something completely different now. Gunnerful. Please tell me this is the right answer. Oh, and I don't have the window showing, sorry. So, I don't know how long. I didn't have the window up. Alright, so that's GNFL. Alright, let's try that now. Oh! So basically the letter swaps don't matter, but that's only because it just so happened that every swapping cycle was a factor of 2, 4, 5, and anything that was divided into a billion. If it was 3, then we would have a bigger issue. But it wouldn't be that hard, but it would be a bigger issue because it depends how many. Depends what. So they were generous. They didn't give us awkward cycles. We just got nice cycles which divide into a billion easily, so they all cancel out. Bloody hell. I spent too long on that question. Alright, ChatGPT. You're up. Will he understand the format of the input though? Yeah, comma separated. Okay, cool. OCID, yeah, that's correct. I mean, that was the easy part. Now, part 2 is the tricky one. But the trick is to ignore the letter swaps, basically. Will ChatGPT know that? He won't know. No, because as I've said, there can be inputs where you can't ignore them, and then you have to do something weird. Well, you do what I did. You create the translation table, and then you have to multiply it up to a billion. But I ended up with the identity function. How does he... I don't like the look of this. Oh, he repeats until he sees a repetition. That actually might work. Damn it, why didn't I think of that? I just assumed there'd be so many possibilities, but actually the numbers work out quite well because it's only 16 letters and the cycles are at most of like 5 or 6 length. So yeah, the lowest common multiple of all the cycle lengths is actually quite low. So yeah, this will work. You don't need to do all the smart stuff I did. Maybe. Let's try it. Oh man, why didn't I think of this? Fuck. Alright, yeah, solved it instantly. Oh my god. That was the biggest disparity between my solution and ChatGPT's solution. I mean, my solution adapts better to longer sequences, because as you get into longer sequences, the point at which they repeat gets exponentially further, basically. Is it exponential? Yeah. Because the number of... There could be a bunch of prime factors of odd, or prime odd cycles. So the lowest common multiple gets very big. In which case, my method is actually pretty good, but small numbers. Wow. How long did that take me altogether? Like 2-3 hours. But I did get very, very stuck. Oh man. So GNFL, need at the end, yeah. But why didn't I think of that? That is actually a very important approach that you need for these problems. Just find the repeat and just use that. I was just too excited by the permutations. I went down the abstract algebra approach. Okay. Well, we've learned something. We've learned... Keep it simple, stupid. Right. Okay, that was a bad attempt at a problem. Like, that took me way too long. All right, 17. Shall I do it? Let's take a look. Spin lock. Interesting. All right, we'll do this. Okay, 1 second. Just need to check a couple of things. Right. Cool. Let's begin. Suddenly, whirling in the distance, you notice what looks like a massive pixelated hurricane, a deadly spinlock. This spinlock isn't just consuming computing power, but memory too. Vast digital mountains are being ripped from the ground and consumed by the vortex. If you don't move quickly, fixing that printer will be the least of your problems. This spinlock's algorithm is simple but efficient, quickly consuming everything in its path. It starts with a circular buffer containing only the value 0, which it marks as the current position. Spin lock. We've got a link to spin lock. It says, I forget what spin lock is. Oh, I remember what spin lock is. It's just an interesting kind of lock, which rotates between different states. Let's not worry about it. All right. So it starts with a circular buffer containing only the value 0, which it marks as the current position. It then steps forward through the circular buffer some number of steps before inserting the first new value 1 after the value it stopped on. The inserted value becomes the current position. Then it steps forward. Okay, fine. Using the location of the inserted value as the new current position, a total of 2017 times. That's not many. So that seems pretty straightforward by brute force. Okay. So it starts with 0, then 1, 0 to 1, so on. Eventually, after 2017... Wait, so the starting number is... What is the starting input? 312. So... Ah, okay. So 3, the example they're using uses 3, alright. So eventually you get a circular buffer looking like that. Perhaps if you can identify the value that will ultimately be after the last value written 2017, you can short circuit the spin lock. In this example, that would be 638. So if we do this the slow way, and then I bet they're going to ask us to do it the fast way for some huge numbers for part 2. Okay, fine. So steps equals, what was it, 317? 312. All right. Number to insert, we're inserting 2017 values. So we buffer equals 0. So for I in range, so it's ix equals 0. Let's say we're sitting on that one. So for I in range 1, okay, so let's carry out the steps. So we step forward, number of steps. Okay, so ix equals ix plus steps percent length buffer. So we're now at the new position. And now ix plus equal 1, so we want to insert after this position. And then we insert buffer.insert at ix, so this could be at the end, the value I. So So the last thing we insert is 2017. And then what do we want in the end? We literally just want IX, because IX will be looking at the new value just inserted. No. It's 1. But it could be circular, so we need to do, just in case, it's at the end. So the next one after 2017. 772? Correct. Okay. Part 2. The spin lock does not short circuit, instead it gets more angry. At least you assume that's what happened. It's spinning significantly faster than it was a moment ago. You have good news and bad news. The good news is that you have improved calculations for how to stop the spin lock. They indicate that you actually need to identify the value after 0 in the current state of the circular buffer. The bad news is that while you were determining this, the spin lock has just finished inserting its 50 millionth value. What is the value after 0 the moment 50 million is inserted? Bloody hell. Alright, I'm pretty sure we are not... just inserting these values. Actually, wait. Yeah, we can. Why not? Just don't use a list. Use the data structure that should be used for this, which is a linked list. I think that's really what you do. Okay. Problem is, $50 million times 300, that's still pretty big, isn't it? Alright, can we think of any speed ups? What is the value after 0? They want to know the value after 0. So the question is, when, how often, and when will we actually return to 0? I guess we don't actually need to store all these numbers then. We only need to store what's after 0. Okay. And anytime we insert something after 0, we replace that knowledge. Then we can just do 50 million, right? We don't care about all the other values, so we don't need a circular buffer. So in the first one, we needed to store everything because we didn't know what would end up after 2017. But in this one, 0 is the first value, so we always know what's after it. Okay, so let's try and do this. So part 2. So ix equals 0. After 0 equals none. There's nothing after... 0 is after 0. Circular buffer. Alright. So, again, we do this... Okay, so we change n here to be... million. So we do this, we just don't change the buffer. So for I in range 1 to n plus 1, I mean, it doesn't, at this point, it doesn't matter what the actual value of I is. So ix equals ix plus steps percent length of buffer. We know what length of buffer will be. That will be... So when I is 0, the length of buffer is 1. So it's going to be I plus 1. Okay. Now, if ix is 0, this is where 0 is. We never actually put anything in front of 0. We're taking 0 to be the start of the array. That's why this works out, because they've chosen 0. If they chose a different number, it wouldn't work. So if ix is 0... Well, if they chose a small number, it would work, but 50 million, it doesn't quite work. So if ix equals 0... then we have a new after 0. Let's go back to doing this. So this is I equals I. Then we add 1. Don't do any buffer nonsense. And then we just print after 0. Is that it? Alright, it's going to do 50 million steps, but that's okay. It's literally just changing an iterator in constant time. Alright. That makes sense. It would be close to 50 million. Correct. That was a nice problem. Actually quite easy, but you have to not fall into the trap of trying to do 50 million buffer updates. That's not going to work because it's going to be quadratic. If you use a list, it's going to be quadratic. If you use a linked list, what would happen? I mean, this would actually work if you used a linked list. I don't see anything wrong with doing that. Linked list will be constant time each step. It's just, it would take a bit longer. And it would take longer to code as well, so no reason to use linked list if you don't actually need to store all that other stuff. But if you needed to know what was after 50 million, then yeah, you probably would need a linked list. So that might have been the better problem to ask, but I don't know. Okay, oh yeah, we need to get ChatGPT on the case. So he'll have no trouble. We need to paste the input as well. Fair enough. I mean, current position is already sitting on the place you need, but fine, you can do that. When you run the program, you get 777? No. Close, but also completely way off because there's no sense of closeness here. But I don't know why he gives these outputs because he doesn't know. He hasn't actually run it. He's just going off what other people have done. All right, so try running his program. It looks fine. $772. Yep, that's right. Now for the next bit. I think he should be able to manage this as well, but yeah, I think he gets it. And no, that's not the answer, but he keeps trying to guess what the actual numerical answer is going to be. Whatever. All right. So yeah, same as what I did. 42729050. Yeah. Okay. Okay. Yeah, it was a nice, easy problem. I was expecting these ones to be a bit harder. This one was easy. Let's go on to 18 then. Yay, assembly code problems. Don't we love these? They're not normally that hard. So, okay. Duet. You discover a tablet containing some strange assembly code labeled simply Duet. As in duets? Okay. Fine. Rather than bother the sound card with it, you decide to run the code yourself. Unfortunately, you don't see any documentation, so you're left to figure out what the instructions mean on your own. It seems like the assembly is meant to operate on a set of registers that are each named with a single letter and that can each hold a single integer. You suppose each register should start with a value of 0. There aren't that many instructions, so it shouldn't be hard to figure out what they do. Here's what you determine. So sound X plays a sound with a frequency equal to the value of X. Sound set XY sets register X to the value of Y. Add. Mul. Okay. Mod. Yep. Cover. So recover. recovers the frequency of the last sound played, but only when the value of x is not 0. So x is... for register. Okay. Okay, fine. JGZ XY jumps with an offset of the value of y, but only if the value of x is greater than 0. Okay, fine. Many of the instructions can take either a register, a single letter, or a number. Okay, I can deal with that. The value of a register is the integer it contains. The value of a number is that number. Okay, after each jump instruction, the program continues with the instruction to which the jump jumped. Otherwise, it goes into the next one. Yep, makes sense. At the time the recover operation is executed, the frequency of the last sound played is 4. What is the value of the recovered frequency? The value of the most recently played sound. The first time an RCV instruction is executed with a non-zero value. So don't need to store all the frequencies, we just keep the last ones. Seems easy enough. It's not that long either. Okay. I think last year's 2016 that had a lot of assembly code stuff. I think a lot of people didn't actually like it. I don't mind it. I think there was some creative stuff there, but many people don't like assembly. People are complaining that you need to know assembly to do it. You do not need to know assembly to do it. This description is completely clear on what all the instructions mean, so you don't need to know assembly. I mean, I remember being taught it in school, but I don't remember anything from school. Wait, okay, I need to copy that. And I did not enjoy it in school. It put me off programming. I thought, oh, this is what programming is these days? I didn't realize, you know, we have higher level languages back then. So I was like, yeah, I'm not interested in programming. And it wasn't until I was like 21 or 22 when I finally realized, no, that isn't actually what people do these days in programming. All right. So we want okay, so just for line in f dot read lines. So okay, let's say instructions equals that. Inst.append, let's say line.strip .split, just as a list, I guess. Okay. So program counter equals 0. We start at the first instruction. We need a register. What registers are being used here? Just these letters. Okay, fine. So register, let's see, equals, I want a default dict for this, because we don't know which ones are being used. Registers equal while I guess while PC is within bounds, even though this doesn't matter, we actually break out of this, but all right, now we just handle each of the instructions one by one. So we say sound X. So we need one value, last sound equals none. Oh, I want a helper. I want a helper method as well. Define get value. Now, this will sort out whether it's a letter or a number. So last time I did that in every if condition. Here we'll just have a helper method. So we'll say if x dot is digit, return x, else return registers x. That way we don't have to keep checking whether it's a number or a letter and dealing with them accordingly. Let's get rid of that S. Alright, so sound X. That should be, and we have to int that because it will be a string. Okay. If int PC, so the first is sound. Okay, then last sound equals get val int PC what? I don't want to have to keep typing this. Let's say z equals int PC. Okay, so if it's set, sets register X to the value of Y. Okay. So register Z1 equals get val Z2. Elif Z0 equals add Similar stuff. Plus equal get value z with 2. Elif z0 is null. Okay, mod change that to percent. RCV. CV. So how does this work again? Recover X. Recovers the frequency of the last sound played, but only when the value of X is not 0. Okay. If Z1, if get value Z1 is not 0, then we're done. This actually what is the value of the recovered frequency the first time an RCV instruction is executed with a non-zero value? Okay, so we break out of this whole thing. And at the end, we print last sound. Okay. All right. 2 more instructions. 1 more instruction. J, G, Z. X, Y. Jumps with an offset of the value of Y, but only if the value of X is greater than 0. Strictly greater then, because you could get negatives maybe? Yeah, you could. So the last one is if X is non-zero, so X could be negative. But in this one, okay, fine. Just a subtle difference. All right. If, so we do this, if get value Z1 strictly greater than 0, then PC plus equal get val Z2. But I want to compensate for what I'm going to do here, which is increase the program counter by 1. So we subtract 1 here. All right, try that. So now it's just going to jump about, do stuff. There was one problem in the past where you had to really look inside these and figure out what's going on semantically in order to know how to cut out loops and stuff, which was quite a pain. So I hope that's not going to be the case here. Looks like it's taking too long. I mean, a single mistake anywhere here could put it into an infinite loop. Alright, we have to look at what's going on then. So I, A, and P. So it goes here. But P is going to be 0, so it doesn't do anything there. Multiply A by 2, so A becomes 2. Oh! That is not digit, but it still should count as a digit. How do we... Let me search this. What's the correct way to do this? Let's try this then. So I want try int s, right? So if there's a value error, then we return register, else return x. That handles the negative case. I guess any other weird stuff. Alright, try again. Okay, that was instant now. Yeah, I mean, I wouldn't expect it to take long. It's part 1. Part 2. As you congratulate yourself for a job well done, you notice that the documentation has been on the back of the tablet this entire time. While you actually got most of the instructions correct, there are a few key differences. This assembly code isn't about sound at all. It's meant to be run twice at the same time. Each running copy of the program has its own set of registers and follows the code independently. In fact, the programs don't even necessarily run at the same speed. To coordinate, they use the send and receive instructions. So, yeah, that makes sense. Sound and recover? No, it's send and receive. Right, so send sends the value of x to the other program. These values wait in a queue until that program is ready to receive them. Each program has its own message queue, so a program can never receive a message it's sent. Receive x receives the next value and stores it in register x. If no values are in the queue, the program waits for a value to be sent to it. Programs do not continue to the next instruction until they have received a value. God. Values are received in the order they are sent. Once both of your programs have terminated... Hang on. Okay, so I understand those two. They reach a deadlock. When this happens, both programs terminate. So if we reach deadlock, okay, I get it, okay. Once both of your programs are terminated, regardless of what caused them to do so, how many times did program 1 send a value? See how to do this. We want to use yields here. It's an interesting problem. So they have their own registers. All right. So define program given an ID num. So we run program 1 and 2, 0 and 1 even. PC equals 0. So a program has its own PC. It has its own register. Instructions is stored here, so now we can do... and the other thing is register P equals ID num. That's the one thing that differentiates these two programs. That will cause them to give different values at some times. So we need a queuing system as well. So collections from queue import queue. So message queue equals we don't want to define it here. The queue needs to be accessible to the other program. Q1, Q0 even. This is for program 0. So we need to tell it where its queue is. So it's given a queue. It's told that's your queue. There's two queues. My queue and other queue. It needs to know both queues. Also, we need to keep a count. Count equals 0. That's how many times we send. Okay, so that's the starting stuff. Now we have to do this whole thing. Okay, now for send. So we need generators, don't we? This is... These are both generators, so we're getting next on... Hello, Zavi boy. Alright, so it's... I'm not sure if I'm doing this the cleanest way, but I guess I need to provide the program with knowledge of the second generator. Have you tried Medlico clone? Did you ever give a link? I don't think I ever received a link in chat. algonewbie.com. Okay. Yeah, I don't think I had the link before. So yeah, I can have a look at that at some point. All right. If okay, let's say Gen 1 is the generator for program 1. Okay, so all these are as usual. So if Z is send, we want to send a message to the other program. So we want other queue dot put that value. That's it. The only tricky bit is receive. Right, receive. So let's say x equals receives the next value and stores it in register X. Okay, so X is Z1. All right, so we have to act differently whether we're program 0 or program 1. If we're program 0, we have to request the next item from program 1. So if id num equals 0, then we okay, hang on. Let's say Q1. We don't care about Q0. Okay. There's no Q0. And that line doesn't even work. Can't. We would need QQ. Alright, so take that out. Okay, so if we send, we do if id num is 0, then Q1, we give that value to Q1. Else, if we're 1, we yield that value. So one of these is a generator, the other isn't. Okay, and now we'll receive. If we're 0, we have to get a value from gen 1. So we do register Z1 equals the next value available from generator 1. Else, if we're 1, so there's two conditions here. If Q1.empty we're actually done. Return. That means deadlock. Q1, program 0 is waiting for something from program 1. Program 1 is waiting for something program 0. So this is deadlock. Else, we just take whatever's out of the queue. So we say register Z1 equals Q1 dot get the next item. All right. JGZ is the same as before. The other thing is this whole process, we're trying to count the number of times program 1 sent a value. So when did that happen? Send. So here, count plus equal 1. Okay, this is a bit confusing. Okay, so now gen 1 equals program 1 Q1 Oh man, this is... I'm not sure I'm doing this right. Okay, Gen 1 is program 1, Q1. So we just say for x in program 0 just do anything, pass, whatever, it doesn't matter. We're just executing it to completion. And then finally we print count. All right, I'm not really good with generators. I don't know if I've done this correctly. 0, okay. Count. So what's going on here? Program. How do you start a generator? I forgot that. Okay, first of all, I don't think you do .get next. I think you do next of Gen 1. Okay, secondly, let's print Gen 1. I don't know what Python thinks this is. Generator object. Good. So for x in program 0 q1 gen 1 pass. So we're waiting on we never yield here, do we? Do we have to... do that? Break? Do you have to use break, not return? Break outside loop. No, break is for inside loops. How do you... see if we're actually getting anywhere. Print Z, print my ID and the instruction we're on. Alright, try that. 0 set I to 31, blah 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 blah. Set mul JGZ. Okay. Set all JGZ. Why does this... Why does this terminate? It should carry on to the next instruction. The next instruction is mul. What would JGZ do? So we don't print that. What? Remind ourselves what JGZ is. So if the value of x is greater than 0, we jump. In this case, it's program 0, so p is 0, so we don't jump. Now PC should be 1 after this. So we go back here. Why doesn't it continue? What happened here? What the heck? So 1, 2, 3, and then it jumps up to that. What? Where on earth did that number come from? Multiply p by 17. Did I get this right? So p... The register p should begin with this value. Okay, fine. So p is 0 for program 0. Multiply p by 17, it should stay 0. What? Let's try printing the register too. So p is 0. How do we jump to that number? Where did that come from? It's... What? So program parameter is 3 here. And then we go to this instruction here, JGZ. If Z1 is greater than 0, I don't know, let's try printing. Print register there. P is 0. If get value of Z1 P key. Oh. Alright, I see one issue. We're not using the right registers. We're not using the independent registers. That's a big problem. So it's holding whatever was there before. Okay, and then here, okay, well, we need to, let's just say R, R, R. Okay, so we just do that. Okay, looking better. Let's take some of this stuff out then. We're using our own private register. Ready num. Okay, so we do set mul jgz mul adds jgz add set mul mod. Integer modulo by 0. What? Damn it. That is using the old register as well. Should have just... Okay, don't use the old register. Should just hide the old register. Generator raised stop iteration. What does that mean exactly? Here we break instead of return. So we break out of this while loop and stop printing stuff as well. Raise stop iteration. What? I mean, that's fine, but that means we've reached deadlock, isn't it? Should we just print count then and see what happens? No. What? Why? What does that mean? Generator raised stop iteration. For X in program, so do we have a return? We have a break that breaks out of that while loop. Do we reach deadlock? I think I see the problem. Okay, fine. So fine, we reach deadlock, but I'm not exiting gracefully. What am I supposed to do here? While... So, okay, fine. If gen1 dot so I don't know, how do you check if there is... Okay, fine. I think what we have to do here is we have to say, I don't know, v equals next gen 1, none. If v is not none, do that. This is the safe way to do it, else break. This is when, so program 1 exits here, program 0 exits here. Oops. There we go. 7239 of this. I hope this is the answer, because I don't really know how I'm going to debug this. I kind of made a mess here. Maybe generators was a bit ambitious. Okay, got it. It was a bit ambitious. We could have just done it with 2 queues and just swap back and forth as necessary. Basically recreating the principle of generators. But actually, now that I've done it, I mean, that kind of makes sense. It's just a bit ugly. No, I think I prefer the generator approach, because it's you're not recreating stuff from scratch, but it's a bit, I don't like having to keep a close check on your own ID, but you kind of do in this case. It's fine. All right, let's see what ChatGPT did then. And I think this is done for the day after this. Oops, I just closed the window. All right. Okay. I don't think he's correctly handling strings and values. He's not checking if it's a string, because I don't think he realized from the description. Eight 600. Yep, okay. I'm interested to see what he does for this. Maybe it'll be a different approach altogether. Concurrency. It's not often that you get problems involving concurrency, but it's an interesting topic to delve into, and you can come up with some interesting problems, like using concurrency. So he's sort of simulating it step by step. He's not using generators. So execute one step of this program, essentially. That's fine. That's how I would do it if this generator method failed. We're going one center value 127 times. Nope. Oh, he spotted a mistake with the deadlock calculation. Fair enough. Shouldn't take this long. That means it's probably stuck in a loop or something. Yeah, I shouldn't take this long. All right, last chance, ChatGPT. I don't have the patience for this. Okay, last chance. Let's see. No. Okay, I'm done with you, ChatGPT, for now. All right, that's problem 18. Yeah, I did 18, so progress. But okay, so I won that one. Okay. All right, I'm done. So this is our calendar now. 1, 2, 3, 4, 5, 6, 7. 7 left, so maybe 2 or 3 sessions more. 3 or 4 maybe, more like. So how do people find these ones? Not too bad. I think people got stuck on the concurrency one maybe. Little drop here, but that's fine. It's a confusing thing. So you kind of just have to know how to deal with concurrency. It's not something that you learn in basic programming. You can kind of come up with it from first principles. It's not that complicated, but it's just... what am I looking for here? Oh, the leaderboard. Yeah, okay. Getting there. Right. That was problem 18. So, either tomorrow or the day after, I'll come back with problem 19. And soon it'll be Christmas Day again. All right, see you next time.